Thanks for the invitation. I'm happy to come here, and this is my first time to come to France. And sorry for those who have been in my talks before, because I'm mostly talk about the same thing, but I will introduce some new developments. So my talk is mostly on the existence question about the constant scalar curvature matrix compact Kähler manifold. So this will be so it will be the existence of constant scalar curvature Kähler matrix. So about the existence questions, there's a very famous conjecture proposed by Yao, Tian, and Donaldson. So it's called the Yao, Tian, Donaldson conjecture, which relates the existence question of constant scalar curvature Kähler matrix to some algebraic stability notion. So it says that CSCK exists if and only if it is k-stable. My work mostly concerns about some analytical criterion for the existence of such metrics. So it is some this analytical criterion is first proposed by Tian. It's called the Tian's properties conjecture. So it basically, roughly speaking, is that, so it says that CSCK metric exists. If and only if there is the associated energy functional is proper or coercive in terms of the distance. In other words, you have the K energy is bigger than equal to C times the distance. Let's call it for now the D1 distance for any Kähler potential phi. So I'll explain the meaning of this conjecture. So the K energy, is also proposed by Mabuchi. So its critical point exactly gives the CSCK metric. It's first defined in terms of its variation as delta K of phi is equal to the integral of delta phi average scalar curvature minus the scalar curvature. So let's call it the scalar curvature of omega phi, right, to n over n factorial. So the notation is that here omega phi is some background metric, omega 0 in this class, plus the dd bar of some Kähler potential. And R omega phi is just the scalar curvature. Of omega phi. And it's possible to write down explicit formula for the K energy. We will do that when we need to. So the whole picture is like the K energy. Okay, so one important fact about the K energy is that it's it's one important fact. Which was first proved by Berntsen, is the convexity of the K energy along geodesics by Berman and Berntsen. So it basically says that the K energy is convex along geodesics. G is convex along geodesics. I didn't explain what is geodesics. So basically, in the space of Kähler potentials in a given class, you can define geodesics between two potentials. And this result basically says that this K energy is convex along such geodesics. Geodesics is convex along geodesics between two Kähler potentials. So that the geometric picture is clear. So it's basically, naively, it just means that a convex function has a critical point if and only if it grows to infinity as the distance moves to infinity. So that's basically, this conjecture boils down to when you just look at the finite dimensional picture. So about some previous works about the previous facts already known. So one direction is already known. So that is the direction where the existence of this metric implies the probability has already been known before. So in this direction, that is the existence implies, existence implies properness. Has been done by a series of works of Davos and Rubinstein. And also Berman, Davos. So, yes. Oh yeah, sure. Sorry, no problem. Okay. So I will write. So the existence part has been proved by Berman by a series of work by Davos and Rubinstein, and Berman, Davos, and Lu. And our work is mainly about the reverse direction. That is how to get the properness, how to get the existence from properness. So the properness implies existence. That is our main. This is our main concern. Okay, so for this direction, it will be. So we will need to. Of course, we need to. So we will prove the existence. So the proof of existence is by continuity method, where you come up with some continuity path and you try to solve the C-stick equation in terms of and you deform a C-stick equation to an equation for which you know the solution. So the continuity path we consider takes the following form. So you consider T times trace omega phi omega 0 minus n equals, or maybe I should put 1 minus t equals t times the scalar curvature of omega phi minus the average scalar curvature, where t is a parameter from 0 to 1. Okay, so first, if t equals 0, then this just means trace omega phi of omega 0 that equals n, and for which we know you have a trivial solution. That is, you can take phi to be just 0. Get a trivial solution. Okay, so then the next question is to show the path is open. So the path, the openness This is by some implicit function theorem, by linearization. And study a linearized fourth order operator. And t equals 0, the openness at t equals 0 is slightly tricky because you are just changing a fourth order equation to a second order equation. That is a little bit tricky, but that's also done. The case when t equals 0 was, I think it was done independently by Hashimoto. And then, okay, so that's the openness part. So our work is mostly how to get the closeness part. So that is to get the existence. So that's to how to prove the closeness. To prove closeness, it will be useful to have explicit formula for the K energy. So for the K energy, you can write down explicitly by integrating the variational, by integrating the derivative of the K energy. And you have the explicit formula for that K of phi. What we need is that the K energy can be decomposed as the sum of the entropy part plus some term plus another, let's call it J part, which you can show it can be controlled in terms of the distance. Controlled in terms of the distance. So okay, we can write down the part explicitly as phi real form of the background metric, wedge j from 0 to n minus 1, omega phi, n minus 1 minus j, wedge omega 0 to the j, plus the average scalar curvature, which is a constant, over n times over n plus 1, I guess. Phi j from 0 to n, omega phi, n minus j, wedge omega 0 to the j. So what do we, okay, so this complicated part, other than the entropy part, does not matter to us. What matters, what we just need to know is that this part can be controlled in terms of the distance. This part just can be controlled by some constant times the distance. So another observation which will be useful for us is that the solution to the twisted equation, that is the solution to the continued path, will also be minimizers of some twisted K energy. Solutions, let's call the twisted equation to be star. So solutions to star minimizes the so-called twisted K energy, that is t times the K energy plus 1 minus t of the j functional, j omega 0 phi. So this part has critical point, so the Euler-Lagrange equation. So the critical point is given by the other part, the left-hand side, trace omega phi, omega 0 equals n. That is, in other words, you have critical point, you have the critical point phi equal to 0. And moreover, it's convex along geodesics. So in particular, this functional has a lower bound. So convex, so we have a functional which is convex along geodesics and has a critical point. Then this functional has a lower bound. Convex along geodesics. So it has a lower bound. Now solutions to this to star minimizes this functional, which means that this functional is uniformly bounded from above. Let's call the solution to be phi t is less than equal to c. Now we already know that the second part is bounded from below, which means that the k-energy must be bounded from above along the path, at least if t is bounded away from 0. So our observation is that, let's say, remember we want to do the closeness part. So you'll say you have ti, a sequence of parameters increased to star. Then we see that since the j part is bounded from above, the k-energy part will have to bound it away from, will have a uniform upper bound. The sup I k-energy is bounded from above. And then we use now we use crucially the properties assumption. So we use here the properties assumption in a crucial way that from here you can get the rest of it. The rest of the k-energy other than the entropy term is uniformly bounded. So you get from properties that the distance function is uniformly bounded. In other words, since k-energy is bounded from above, that is the whole complicated thing is bounded from above. And also we know that from kind of elementary calculations that this complicated term is just bounded in terms of the distance. Then we just know that the entropy term is uniformly bounded from above. So this again implies the uniform bound on entropy. It's less than equal to c. And then after we get the entropy bound, that's when the regularity theorem comes in. So here's the regularity. So the regularity theorem says that suppose you have scalar curvature. Consider equations of the form scalar curvature equals eta. Let's call it r plus trace omega phi of eta. Because we want to apply the estimates to the twisted equation, so you have to consider more general equations than the CSAK. But that doesn't change the estimates much. So we consider the equations of the form, the scalar curvature equals some bounded function plus the trace of bounded 1-1 form. So R is a bounded function on M, and eta, let's call it smooth. You can assume it's smooth. 1-1 form on eta. Sorry, on M. Yes, maybe I will need to choose smooth and closed. And then the estimate states the following. Suppose you normalize the potential so that sup equals 0. Then you have uniform estimates up to W4P. Is less than equal to constant, which depends on P. And also depending on the absolute bound of the function R. That is the C0 bound of the function R. And also the C0 bound of the 1-1 form eta. So then once you have this W4P bound, then you can use the standard elliptic estimates to get higher derivative bounds, and then that gives you the closeness you want. So, and next, I will explain about those estimates, and also I will discuss some questions one can consider next. Okay, so maybe I can put this down. Okay. Okay, so steps to get the estimates. So here are the steps to get the main estimates. So the first is the entropy bound. That is, the entropy bound means the entropy bound means the bound for the integral log omega phi to the n over omega 0 to the n times omega phi to the n. So entropy bound means a bound like this. So the first step is to get the entropy bound for implies the upper bound for the volume ratio. And the next is that from volume ratio bounded, for using the Claudius C0 estimate, we get C0 bound for the Kähler potential. So phi to n over 0 to the n implies C0 bound for the potential. This follows from the work of Collodi, for which actually he just needs the volume ratio to be LP for P bigger than 1. And then once you get the Kähler potential is bounded, then you can get the lower bound for the volume ratio. Apply that. Phi n is bigger than 2 over C. Okay, so once you have the volume ratio bounded from above and below, then you get the second derivative is in LP. So apply that. The second derivative, Vij bar, LP bound, has LP bound for the complex Hessian is LP for any finite P. And then you go from the LP bound for the second derivative to the gradient bound of the volume ratio. So part 4 says that to use the LP bound for P big enough depending on dimension, then this gives a gradient bound for the volume potential as well as absolute bounds for the second derivative. So that it is called Laplacian phi of omega phi log plus Vij bar is the same to C. And then after you get this second mixed, the complex session is bounded, then you can just use standard estimates to get high regularity. 5 standard estimates to get high regularity. For higher regularity. Okay. Okay, so I will take the time to maybe I'll take the time to explain about the first estimate, and that is probably the most the most tricky part. Okay. So let me sketch the first step. So the proof for this first part is like a mass concentration technique. It's like you solve. So the mass concentration technique means that you solve an auxiliary problem and use that as a comparison function. So it means in our setting it means that you solve an auxiliary function psi. Okay, so let psi solves the following problem: omega psi to the n equals e to the f square root of f squared plus 1 divided by, sorry, I forgot to say that f squared plus 1 omega 0 to the n, where f is just the log of the volume ratio, where of course you can normalize so that the sup of psi equal to 0. Okay, so this problem is solvable because of by Yao. And then we use this as the comparison function. Then we use then the key to prove our result is to prove that for any epsilon positive, you have the bound f plus epsilon psi minus some, let's write it the constant explicitly, twice the Ricci bound plus 1, let's say phi is unbounded from above. So you have this estimate. Of course, the constancy will depend on epsilon. Once you get to this, then you can so once you get to this, you can let any q bigger than 1, and then you multiply this to q, multiply this by q on both sides. Q times f is less than or equal to negative epsilon q psi plus twice c omega 0 plus 1 times q phi is less than q times c epsilon. And then you raise both sides to the exponential. So e to the qf. So you raise both sides to the exponential, less than e to the negative epsilon q psi times e to the q c epsilon. So here we use that phi is non-positive because we normalize that sup equal to 0, so it's non-positive. So the e to this thing will be less than 1, so you just drop it. So then you get the LQ bound for the volume ratio. For e to the volume ratio is bounded by e to the negative epsilon q psi. Then we choose epsilon small enough. Choose epsilon small enough so that, and then we use the existence of alpha invariant. So I use the alpha invariant, then so that epsilon q is less than alpha. Here is the alpha invariant. So it says that, so it basically says that for any phi prime, which is P subharmonic with respect to omega 0, you have, so there exists some alpha which depends only on the class. So that for any PSH function, you have e to the negative alpha phi prime minus sup phi prime is bounded by a universal constant. So this is I first see this result in the paper of Tian. So once you choose epsilon small enough so that epsilon q is less than alpha invariant, you get an integral bound on the right hand side, and so you get a LQ bound for the exponential of the log volume ratio, and then you can use the Claudius estimate. Then you use Claudy. So then we get, so that is you get integral e to the qf is less than equal to c of q depending on q. And then you use the Claudy estimate. That will give you that psi and phi are both bounded. So you get the upper bound for the volume ratio. So that f has an upper bound. So we will see how to get this key estimate. Okay, see. So how to get the key estimate? So here psi solves this problem, and then we will do the following calculation to get the key estimate stayed here. So we will let delta to be a small constant. And then we compute Laplacian phi of the quantity. Let's call it u, let's denote u to be that thing, plus epsilon psi minus twice Ricci bound of the background metric plus 1 phi, and then we compute delta u. Then delta phi is just a Laplacian operator of the metric omega phi, so you write this in coordinates. E to the, and then you compute this Laplacian, and then you find that you get delta square gradient phi u square phi is the delta u delta Laplacian phi of u. Okay, so then we will have to find what is Laplacian of u. Phi of f plus epsilon Laplacian phi of psi minus twice omega 0 plus 1 phi. Okay, so for the Laplacian phi of f, we have to use the equation. Okay, so the equation says that the scalar curvature equals a constant. Now the scalar curvature is by taking the trace of the Ricci, so it gives and you know that Ricci of omega phi and Ricci of omega 0 is in the same class, and the difference differs by the dd bar of the log volume ratio. And this gives g phi of Ricci 0 minus dd bar f. So that is, this gives the trace of, trace omega phi of Ricci omega 0 minus Laplacian phi of f. So in other words, you can take this Laplacian phi of f to be, this equals negative average scalar curvature plus trace omega phi of omega 0 plus epsilon Laplacian phi psi minus twice Ricci 0 plus 1. Laplacian phi you can compute, that is n minus trace omega phi omega 0. Okay, so then it only remains to compute what is this. Okay, so for that, Okay, so you have to again go back to the coordinates. Laplace phi psi, again by definition. This is g psi ij bar. And then that is, sorry, no, there's no g psi. So what I want is to write this g psi ij bar minus g ij bar. So you get psi ij bar. And then you get, so then you use the arithmetic geometric inequality. This is bigger than equal to, it's bigger than equal to n times determinant. So we can compute everything in terms of everything just on local coordinates times determinant of g psi lower ij bar to the power 1 over n. And this minus part is just the trace omega phi in terms of background metric omega 0. And then you use the equation for psi. Let's just call this bound to be A, which is a constant under control because you assumed entropy bound. So this gives like n times at a to the negative 1 of n, which is a constant under control. And this gives f squared plus 1 over 2n minus trace omega phi omega 0. Okay, so it basically gives that, so let me just summarize the whole calculation. So Laplace phi of E delta U is greater than or equal to some constant, let's say epsilon 0 times f squared plus 1 to the 1 over 2n plus trace omega phi omega 0 minus c. Okay, so once you get to this, then you do a cutoff argument near the point where this function u achieves max. So let p0 be such that u achieves max. So basically you let eta to be the function so that this is p0. And you take a cutoff function for which it equals value 1 at the point. And you take a ball so that it is slightly smaller outside the ball. So here it takes the value 1, and here it is slightly smaller outside, is 1 minus theta, where theta is another small parameter you have to choose. And then you have to choose theta to be small enough so that you do a cutoff using this function eta. And then you compute Laplace phi of e to the delta u times zeta. This will be bigger than epsilon 0 prime, another small constant, plus 1 over 2n minus c prime. Okay, once you get to this, then we use the so-called Alexandrov maximum principle. Okay, so then you use the Alexandrov maximum principle. So that you can conclude in the ball. So we have just chosen a ball near the point where this function achieves max, and then you do the Alexandrov maximum principle there, and then you get soup over the ball is controlled by the soup over the boundary plus the integral c depending on dimension times the diameter. And extra term is just the right-hand side to the power of the dimension. That is the negative. So that's the negative part of Laplace phi of u sorry, actually I should use it with e to the delta u. E to the delta u. Sorry, it's like the Laplacian phi of e to the delta u, the negative part to the dimension 2n divided by determinant of the G phi Apriori G bar, which is a coefficient matrix, to the which is just the dimension matrix to the power 2n. Actually, it should be the whole thing to the power 2n. D volume G, take the norm. Actually, I forgot, this should be whole thing times e to the delta u. Okay, so the point is that on the boundary, because of the choice of the cutoff function, this is, so for the left-hand side, it's just a soup over the whole manifold. And on the boundary, it is less than a small constant times the soup on the whole manifold. So you just need to bound this integral. And for that integral, you find that you just need to take the part where the right-hand side is negative. But when the right-hand side is negative, you get the upper bound for f. So you get a bound for every term in this integral. So I'm a little bit waving my hand. So this gives a constant depending on epsilon 0 prime times integral of e to the negative delta times the 2 Ricci bound times phi. Again, here you just use the definition of the function of the quantity u is here, and use that psi is non-positive, so you drop it, and also then the term you need to, so, and also for the f term, that's under control because we just integrate on the set where f has the upper bound. And also, so the only thing you need to worry about is the e to the negative exponent here. But here we have e to the negative, negative exponent is e to the negative delta times some universal constant times phi, which can be bounded using the alpha invariant by choosing the delta small enough. So you get the bound for the whole integral, and you get the bound for the function u. And that's the key estimate. Okay, so that's kind of the tedious part. So maybe I don't have much time left, but I hope to mention about some natural questions which arise. 3 minutes, right? 10. Wow. Oh yeah, that's great. I thought now it's 47. So yeah, I can definitely mention some of the the direct results, and also natural questions which come out of this. Okay, so I can no longer use that. Maybe I can. Okay, so now I'll explain some natural questions one can consider. So just some remarks, maybe. So maybe one can consider how to get the so now it only remains to see how to get these properties from the algebraic stability, which is unclear for now. And also another natural question is that whether these estimates carry over to the parabolic case. That is, does this work for Calabi flow? Unfortunately, none of those estimates works, at least so far as I tried. Okay, so first, none of those estimates works for Calabi flow. Well, at least as far as I can see. None of those work for Calabi flow. by Calabi flow, I mean just the flow version of the elliptic problem. So Calabi flow means you have this parabolic equation dt phi equals the scalar curvature minus this constant. So none of those estimates carry over, and essentially it just looks like a mess for now. Okay, the next question is maybe is less exciting than this. How about the boundary value problem? Maybe this may be of interest purely from PD point of view. Actually, this is not hard to. This is not a hard problem as long as you pose the correct boundary condition. So the boundary value problem, can be solved if you prescribe boundary values for the Kähler potential and volume ratio. On the boundary. Okay, so yeah. Okay, so so for now I have to assume the prescribed scalar curvature is non-positive. So prescribed curvature is non-positive. Then you can solve such a boundary value problem. Okay. Okay. So yeah. So actually, there's a recent development. Is that okay? So another remark I wish to make is that it is like a direct consequence of the provenance theorem that you have. That the existence of CSK is equivalent to the so-called geodesic stability. So maybe I can erase this. Okay, so another remark is that it's like direct. This kind of direct consequence is that the existence of CSK is equivalent to geodesic stability. What this precisely means, geodesic stability, it means that the K energy has positive slope along all the geodesic rays. So in this roughly speaking, it means that geodesic, so the K energy over the distance phi t as t tends to infinity has a lower bound, so that means the K energy has positive slope along all the geodesic rays. So here, t is from 0 to infinity. Okay, so here phi. So here it is for our purpose. It's important that so we are only able to get the stability in the weakest possible sense. So that is here the geodesic rays are just L1 so the potential is only L1. It's a kind of a weak geodesic ray. It's not smooth. The potential is not smooth. So it's just a weak kind of weak geodesic ray for which the potential is only L1. So along weak geodesic ray. So roughly speaking, that's phi of t is only in L1. So precisely, I think L1 has to be in terms of the background volume and also the volume defined by the Kähler potential. So, and I think there's a very recent preprint which says that you can actually replace all the geodesic rays. Not just you don't have to test all the weak geodesic rays. You can just test against along those C11 geodesic rays. So this is a recent work by I think by Davos and Lu. So it says that they basically says that equivalence. So it says existence is just equivalent to geodesic stability only for C11 geodesic rays. C11 rays, which means that along the ray, the potential has bounded complex hashing. So their improvement says that it suffices to consider such rays with good regularity. Okay, so maybe I'm running out of time. Yeah. So maybe I should stop here.
Very briefly, maybe I've missed something, but in that inequality, how do you get the 1 minus theta supremum? How do you know that the supremum over the boundary is uniformly bounded by?
Oh yeah, so that's my bad. So I don't use the extent of maximum appearance directly to E delta U because you have no control over the boundary, right? So that's why I use some cutoff function eta, which is slightly smaller than 1 on the boundary. So actually it should be eta here, where this ball is centered on the point so that this E to the delta U has max. So on the boundary is slightly smaller. You have to make sure on the boundary is slightly smaller so that it gives you something. Otherwise, you have no control over the boundary and then it gives nothing. Yeah.
Other questions? Okay, I do have one, maybe a technical one, I don't know. So do you need, for your step 3, so to get the P bound for the Hessian, phi ij bar, do you need a gradient estimate, so uniform estimates for the gradient of phi?
No, well, for the first version, we did gradient estimate, but you can actually skip that step.
Okay, so this was my question. So you can go around.
Yes, right. You can go around the gradient estimate and go directly to the second order.
Maybe you can explain to me that later.
Yeah.
Okay, so shall we thank Jingrui again? Thanks a lot.